Let's explore torque and lever arms, two fundamental ideas in rotational motion. We'll start with the concept of a lever arm. A lever arm is the perpendicular distance from the axis of rotation to the line of action of a force. Take a look at the diagram below. You'll see a lever at an angle. There's a labeled force vector, F, pointing upward and to the right. A dotted line extends along the direction of the force. The lever rotates around a pivot, or axis of rotation, shown at the left end. The angle between the force and the lever arm is labeled theta. The lever arm is shown as the perpendicular distance from the axis of rotation to the dotted line representing the force direction. This distance is what we use when calculating torque. Now let's define torque. Torque is a measure of how much a force causes an object to rotate about an axis. You can think of it as the rotational version of force. It's a vector measured in Newton meters and represented by the Greek letter tau. Now refer to the equation below. Tau equals r times F times sine of theta. Tau is the magnitude of torque. R is the position vector, the distance from the axis of rotation to the point where the force is applied. F is the magnitude of the applied force, and theta is the angle between the position vector and the force vector. When theta equals 90 degrees, sine of theta is 1, and torque is maximized. That's why perpendicular forces are most effective at producing rotation. To help visualize torque, let's look at a force diagram. Refer to the next image. We have a horizontal lever that's 20 centimeters long. A 10 Newton force is applied at the far end, but at an angle of 30 degrees above the horizontal. The axis of rotation is at the left end of the lever. The force vector originates at the point of application and points up and to the right. The angle between the force and the lever is clearly labeled. From here, we can calculate torque using the equation. Tau equals 0.2 meters times 10 newtons times sine of 30 degrees. This shows how force, distance, and angle all work together to determine the rotational effect.